anything on Mondays. I just don't have any lectures that day. So Tuesdays always feel like a Monday to me. So I'm pretty much always going to start on a Tuesday saying, how are you guys? How was your weekend? Things like that, because I almost started in on that just now. So to go ahead and address it, that's why that's going to happen. Hello, and pleasure to meet most of you and see some of you again. I am Joshua Hoffbauer, and I'm going to be the instructor for this semester section of Physics 1510. This is the H lecture. There's also excuse me. I have two sections of 1510. This is the second of them. That means there's a different lecture that you can also sit in on if you miss one or need to want to just sit in to re-listen to something. So that means that there's 7 other students doing the same thing that you might have labs with, that you might be taking tests with, working on the same homework with. I actually encourage you guys to work with each other in the other section because you're all doing the same homework anyway. Might as well help each other out. So, good day. I'm meeting most of you for the first time, I believe. Welcome. I'm operating on the assumption that most of you are coming directly from Dr. Odekor's 1500 last semester. Mostly nodding. Okay. So 1510 is the direct continuation. So the physics is the same. This is the next step in terms of the physics. Some things are going to be a little different though. First of all, you're inside. Second of all, I'm not Dr. Odekor. But I was his student. I actually came here as a student and got my physics degree from PC. And Dr. Odekor was one of my professors, and sorry, he was not my main advisor, but he was my project advisor on my final project and my honors project. Honors society, no. I stumble over my words a lot. Let me go ahead and warn you. Not honors society, but like honors day project, that was it. So, I am not him, but because I learned from him, there's still going to be a lot of commonisms between the two of our teaching styles. And I'm going to try to make the transition from one to the other, from last semester to this one, as smooth as possible for you guys, because you're here to learn, not be jarred by different teaching styles. So I am going to make this as effective and easy a transition and a semester for you as I possibly can. Because physics is hard, even when there is a virus. We will be having class in here just because I prefer to have the consistency of the inside. Additionally, there's very few of you. There's 7 in this lecture, 7 in the other. So, as long as everyone doesn't sit at the marked off taped seats, we should be fine in here together. The tape does represent the seats that shouldn't be used, although I suppose if everyone sat on the X's instead of the blanks, it wouldn't matter one way or the other as long as we stick to a pattern. And I guess if you all take opposite corners, then it really doesn't matter anyway. But those are there as a precaution. Masks in class. If you need to miss a day for any reason, be it sports or health related, that is fine because I don't take attendance. Your job is to learn, and some people can do that when they're not here. I do record the lessons, so there's a camera in the back there, hello internet. And those recordings are available if you miss a day or if you just need to re-listen to something. Let's see, differences from before. Okay, things that are the same is, again, it's still the same physics, it's still the same universe that you're studying. Keep all your notes. Excuse me. My first 2 years at PC here were all in the same notebook, and I still have it. It's a direct continuation. I recommend just continuing on from the same notebook, unless you have a very specific filing system. I'll leave it up to you guys, but at least keep them. We're also going to still be using WebAssign. It's the same textbook. We're still going to be sort of jumping around chapters in that book, but same homework software, same types of questions. at least given in the same kind of a format, asked in similar ways. A couple of things that are different is what we're going to be talking about. It's still the same universe, but we're looking at different parts of it. 1500 was mostly about sort of physical and mechanical things you might have noticed. Forces, movement, how energy affects movement, how we do work in a physical space with mechanical energy. This class is going to be a little more abstract because we're going to move on to the things that are slightly less tangible. The first chunk of the course is going to be about heat thermodynamics. We're going to spend about a month and a half on these categories, and our first test will just be on these common principles. Second sort of chunk is electricity and magnetism. Pardon me. Another fun quirk about me is I drink a whole lot of water, stay hydrated. Second chunk, electricity and magnetism. This will make up the second test. About 2 months on this. There will not be a test on waves, sound, and light because this will be covered in like the month or weeks leading into the exam. I don't want to cram another test in right before exam season. So we're covering these because they're important to know. This defines everything about how you see and hear. But those will be folded into the exam. 2 tests, one on this, and then an exam containing everything. I have a million points to make and forget what order they need to be given in. Any questions so far? Okay. I know the first day is always the most exciting part, is we're just going over logistical information. And in a lot of ways, this is the same kind of class you've already taken, so I don't want to be a leader at the point too much. But some advice to give you, which you probably heard a lot of it before, but I think a lot of it bears repeating because people tend to forget not to panic. Physics is hard, and it's okay that it's hard because we're trying to study the entire universe. But my philosophy is, you guys you basically already know all this stuff because you've been watching it happen your entire lives. The world runs on electricity. You literally see and hear with waves. You're a warm-blooded organism that produces heat and that interacts with the things you touch around you. All of the concepts you talked about last semester and this semester are things you're familiar with. It's in your head, you just maybe don't put words to it. The way that I want to teach is to help you understand what you already know and just put the words to it. Because even if you never do the math from this class again, you still live in a universe where all this stuff happens, and I want you to understand it to just help you in whatever you do. Something I personally encourage everyone to do is please ask questions, because if you don't get something, I want you to stop me then so that we can clear it up and I can help you with it then. Because if I continue on, it's just going to be more confusing things on top of the thing you already weren't doing so well with. We are in lecture and I'm going through I'm going to be pointing my hand a lot, saying a lot of things very quickly at you. I want you to stop me. There's a few people in here where you can just interject. It's okay. I want you to do it. Because odds are someone else is confused too. And odds are they're also nervous and not saying anything because I'm just saying words and they don't want to interrupt. Please cut me off. I am asking you. Additionally, never leave a question blank on any assignment, because that's the only way it's going to be worth 0 points. We're doing more and more digital assignments these days for the quarantine reasons. But on digital tests, I still want you to send me pictures of your work. Literally anything written on any question is worth some amount of points. Just put some amount of work into it. The only way to get a 0 is to leave it completely blank. So try everything. It'll help you learn, because just writing out the first part gets the process going at the very least. And I lose my train of thought a lot. I don't do it so far. Okay. Like I said, physics is hard. That's still going to be true, but your job isn't to bang your head against a wall right here. Your job is to understand it and pass the class. My job is to make sure you get there, and I'm going to do my job. So my promise to you guys is I'm going to help you with the transition from the last semester to this one, and I'm going to make sure this is an effective class for everyone, where you can all get through it in one piece. Cool. Okay, now, like I said, I'm not Dr. Rochefort, so this is me, and that's my fiance hiding nervously behind me. Her name is Lula, and again, my name is Josh Hoffbauer. To address something that comes up in emails, at the start of every semester, students will email me questions like, do we have lab this week, or textbook, homework, syllabus stuff. And they always, before they meet me, assume Dr. Hoffbauer. I don't actually have my doctorate yet, so I'm only addressing that now because I don't want to accidentally make people think I have it when I don't. So I'm technically not Dr. Hoffbauer. A lot of my students call me Prof. Hoff, but instead, put any variation of Mr. Professor and some variation of my last name is acceptable. It's pronounced Hoffbauer, and most people just stop after the F. I was a PC student. I started in 2010, graduated in 2014 with a major in physics and a minor in mathematics. Despite that, I'm still not good at mental math. I'm very reliant on the same calculator I've used since middle school. And then did 2 years at App State, got my master's in engineering physics, and that was where I started being paid to teach people. Well, no, I worked as a tutor here at PC, but that was walking around money. At App State, I was actually paid enough money to buy food, rent, to teach as a teaching assistant, and that kind of got teaching warm in my brain. Because after App State, I went to work a normal engineering job, and every day I was just thinking, teaching was a lot more fun than programming lumber mills. So now I teach physics, and I'm actually very happy to be back at PC because I just like it here. One of the things that I really liked and still like about this school is I find it easier to be able to connect with people. I like getting to know my students because it helps me to know how to teach them. Because if I know what you're having trouble with, what you're interested in, it helps me re-explain things, tie things back into what you're interested in the way that you need to be able to understand it. It's a little harder these days because there's a decent chance I will never see any of you below your cheekbones, which is frustrating. But I still want to at least attempt to foster that same kind of an environment. So to help with that, I have a policy where I want you guys to ask as many goofy science and sci-fi questions as pop into your head. Because if this ends up being the last time you take a physics class, you might not be able to ask someone else the scientific validity of Star Wars. And if I haven't seen a particular movie, I can at least talk something about it. I grew up in a Wars house, not a Trek house, but I know enough about Star Trek to talk about it at least to tell you what does and doesn't work. So I want you to ask those kinds of questions. Any random thing you saw on TV, heard in the news, could possibly be tied into science, do it, because I can make something fun out of it with you guys. I am also just a big goofball. I I'm currently working amateur on writing some things and doing a little bit of acting and voice work. So I do impressions, which doesn't happen organically in lecture a whole lot, but occasionally a voice, you might hear a voice that isn't natively mine if it comes up. And I just want to try to make this an enjoyable time for you guys. So anything I can do after that. I'm also, like probably every 5 minutes, I might default to, do you guys have any questions? I'm going to say it a lot. It's going to get annoying, but it's going to happen because I want you to ask them.
Is your self-aware?
I try to be. I find that to be an important trait because denying my flaws doesn't accomplish anything. Speaking of self-awareness, any questions? Okay. Additionally, weakness of mine, I am just awful with names. I'm very good at faces, and you can tell me everything about yourself, and I will remember that information with your face, but there's a pit in my brain where all the names go. I don't know why. That's the one thing about people I can never remember. I'm just warning you because it's going to be a problem, and I don't like it about myself that it happens, and I'm going to work on it. It's a very small class, so I should get to know them all by the end. I do apologize about it in advance. I am trying, I promise. I think I spent up too much of my brain capacity remembering the names of all the Pokemon. I love the 90s. So, the syllabus is going to be incredibly similar to the one that you already have for previous physics classes. I don't want to beleaguer the point too much. But the syllabus is going to be on the Brightspace page. I'm trying to cut down on needless handing out of paper from person to person these days. So it is currently on Brightspace. If you can't access Brightspace, please let me know because that needs to be fixed quickly. We've had a couple of glitches with the Brightspace page, so I want to address that really quickly. Come on. I'm going to back up just a second. Now, I mentioned that I have 2 different lecture sections of 1510, and each of those lecture sections actually has 3 different lab opportunities. So when you signed up for your courses, you picked from like one of 6 options. The way that Brightspace works by default, it made a separate classroom for all 6 of those options, which I didn't want to deal with because you're all doing the same assignments and learning the same things. So my goal was to compress them down into 1. And I think it's worked, but sometimes one of those defunct sections pops back up. So if you're in one of those defunct sections, it will have a similar name, but it will specify like EX or HY or something, and it won't have all the files I put in it. So if yours has a slightly different name to this, it should be Pop Hour General Physics 2, Spring 2021. If it is slightly different to that, and it doesn't have these 2 tabs in it, it's the wrong one, and I can make sure you end up in the right one. I just need to know who isn't there yet. I think everyone is, though, because I think it was listing people in both by default, so it shouldn't be a problem. I'm just paranoid. Click on the tabs, and all the information is here. Course info contains syllabus and that introductory slideshow from a second ago. So that's all there for you guys. The syllabus, again, is very similar to what you've seen before, so I mostly just want to focus on what would be different. Firstly, that's my information there at the top now. Got my email address, which is most of my full name. And this website is to the YouTube channel where I upload the recordings from the lectures. So you can go here as you see those if you need them for any reason. The channel is very boring, but that's where they'll be. Although all of these are old, these don't apply to you guys. There is some stuff from previous times I've taught 1510. If you really want to dig through the backlog for like another take on the same lecture, boy, that is highly optional. I wouldn't really recommend it. Okay, this room is 1510, so if you see that number, it means this classroom. This number is my office. My office is in that little alcove. If you turn left out of this room, right like you're going to the green out the middle doors. And then there's this weird little nook off to the side there with like 3 offices and a fridge and a table in there. I'm one of those offices, and I've tried to. I have not found a good way to verbally describe where that is. That's the photos and the poorly drawn arrows. It's 103B, and my door does have my name on it, so I hope it's not hard to find. If I am not in this room or in the lab room, I'm probably there, or I've left campus. So if you need anything, you can come find me somewhere on this floor, or you can email me. My address is up the top. You're going to be receiving many emails from me over the semester, so you will have that email address. And I know many professors' inboxes are just a swamp that nothing ever gets out of. I try to make it a point to answer emails very quickly. They route directly to my phone, so I have no excuse. If I want you to email me your questions, if I don't answer quickly, it means I'm driving or asleep. I'm trying to make it so those are my only 2 excuses. Or church. Or talking to Lula. But I will get back to you quickly, I promise. Class times and sections. This is section H, so we meet twice a week for an hour and 15 minutes, which I think is a long amount of time to just be listening to physics. So about halfway through, I usually like to declare a water break. If for no other reason than I usually run out. 3 different lab times. It's all the same lab though. Whichever one you signed up for is just the one that you are slotted to attend. But it's the same lab each day of the week. It's just a matter of when you show up for it. So if your schedule says HW, it means that you attend the H lecture and you would come to the W lab. Speaking of, no labs this week. We're still getting started. I'm still figuring things out. So we'll resume labs next week. That means that there's no lab assignment at all, and you don't have to come to the building during your lab time this week. Just know which one you are supposed to be signed up for, but if you need to attend a different one because of weird scheduling things for a week, that is fine. You could attend a different one to make up a lab you missed, or to avoid missing it. I don't really care. There's not going to be many students in each of them because it's 3 sections for a total of 14 students. So there's going to be lots of space for everybody. We've got grading scale, grading rubric. Homeworks and quizzes are still a very small part of your grade. Do them, make mistakes on them, they'll be fine. You could technically not do any homework or quizzes and still get a B in class. Not that I recommend that approach. Same textbook, same WebAssign. Oh, okay. Same website for WebAssign, but you need a different access code. And here is that code. If you don't have your laptop in front of you or just won't have this page up anytime soon, this is the access code. And when you get into WebAssign, it should look something like, why did I get signed out? Cindy H hates me. 10 gauge hates me.
I hate to see it.
There we go. Now it works. Okay, you input that code. It should look like this, Physics 1510, section E and H, because it's one web assign for all of my students. These two assignments are already live. Make sure you can see them. They'll be due in 2 weeks. You don't have to worry about them anytime soon. Just make sure you can get in there and start looking at them. Let's see. Lectures will be in here unless we need to, unless the school breaks for quarantine for any length of time. But again, still recording them in case you need that backup. Please come to class. Please ask questions again. I beg you. Labs. Labs. I have been told Dr. Rodicor had a very interesting system for lab times last semester, which I applaud him for the ingenuity, but there's far fewer of you this time around, which makes the need for that a little less extreme, I feel, because each section currently only has like 4 people in it. So and 2 groups can be on other ends of the lab right now. It's a very small room. But it'll be the same room. It's still 126, which is that lab at the end of the hallway if you're going towards the bio building. So my plan for right now is to default to the usual sort of PC lab style where you come on your assigned day and you have 3 hours. Most people finish in about 1 or 2. So that might be a little bit of a change if you haven't had any other labs around here yet. But all of my deliberation and analysis says that should be fine for what we need for this particular class. The setup will be in there. I will be in there myself to oversee things and give a little intro lecture at the beginning to make sure everyone knows what they need to be able to use all the equipment. Equipment will be cleaned between uses, and everyone will be as far apart as they need to be. So, normal for this school's labs, but I admit maybe a little different from last semester. Any questions about that? Okay. Homework and quizzes are going to be on WebAssign. Should be very, very similar to how you did in the last semester. But just in brief, the way that I do the homework is I put up the assignment so that you can start looking at it as soon as we begin the chapter, probably even a little bit earlier than that. I encourage you to open it, look at it, at least look at the questions so that you know what you don't know yet. And it'll be due, we'll do about 1 homework and 1 quiz a week, so I encourage you to start at the beginning of the week. You have over the weekend to finish it. I usually like making it due on Tuesday night so that after you work on it over the weekend, you can come in and ask questions on Tuesday. So I tend to make those due on Tuesday, the homework and the quiz. They use the same standard sort of WebAssign system. You open it, the homework you have as much time as you need and as many tries as you need. The quiz, when you open it, you have an hour to finish it, but they're designed to take like 10, 20 minutes. They're both low stakes practice. These are the assignments to make mistakes on. That said, WebAssign is not always user-friendly. Sometimes it makes mistakes. If you feel like the computer is doing something wrong here, let me know. I can check it and fix it from my back, the tools that I have. I will make the machine act right, because the machine uprising is really just them being super passive-aggressive against us. Homeworks will be about 10 questions, 1 per week. Quizzes will be about 2 to 3 questions, also 1 quiz per week. I encourage you to work with each other and even the other lecturer if you have friends in there on your homework. That is the time for you to work together, make sure everyone understands it, before you use the quiz as sort of like, can I do this on my own practice? I always recommend doing the quiz last. Do the homework, make sure you understand the homework, then do the quiz before it's due. You will have a total of 2 tests, and I will tell you when those will be very soon, so that you know about them. I just haven't finished picking the dates yet, but I will tell you them in advance so that you know them. And as a general rule, I will never give you a test or an assignment. I will never make them do earlier than they were. I will never move an assignment up. I will only ever push it back. So if I'm going to tell you test dates, sometime this or next week for both of them for this semester. But if they need to change, I will only ever delay them. Okay? Which is why I really need to do my math very right the first time. Right now, the system I'm moving forward with is that the test the test will be given through WebAssign, and you'll submit the numerical answers through WebAssign. It'll be kind of similar to a quiz. You open it, and you'll probably have 3 to 5 hours to input all of your answers, so that you have time to go to the bathroom, take a break, get some water. And to account for the fact that you're going to be sending me your your questions remotely, because everything takes longer through email. So it's designed to take you 50 minutes, because that's what a normal class test should be. I'm giving you longer than that because of all the obstructions we're dealing with. You'll have like a couple of days to decide when you take it. I'll put it up at like the start of the week, and you can pick between the start of the week and the end of the week when you do it. You can email me your questions and I'll answer them as quickly as I can. I also encourage you to send me pictures of your work when you're done, because normally, if we were doing like a departmental test where all the students would be in one room taking it, I'd have your work with me and I would give it partial credit. So even if the answers are going into WebAssign, I still want to see what you did for your work, and I will adjust what WebAssign gives you as a grade based on it. In fact, WebAssign won't even tell you your grade, because it's going to be wrong. Because if you don't get any of the answers right, but you still did the work, you could still get a 90. But WebAssign wouldn't say that. So WebAssign won't even give you a test grade. I will manually input it and then tell you when you can look at it. So I grade super well for partial credit. Again, literally anything written is better than nothing. And since you're sending me pictures of the work, if you have no idea what to do for number 5, just take a piece of paper, write number 5, and then draw a smiley face on the page. That's some amount of work. That's at least 1 out of 20 instead of 0 out of 20. The exam will probably work very similarly through the WebAssign, just to keep people from having to be in the same space as we're trying to end for the semester. It'll be longer than a standard test, but it'll probably work very similarly in terms of WebAssign, send me your work afterwards. I might have to ask everyone to be on camera at the same time, taking it at the same time, but it'll still work the same way, and you'll still get partial credit for your work. Please ask questions, please work together. Make sure you can log into Brightspace and WebAssign. I've been talking a lot and need some water. How are you guys doing? Any questions? I'm nodding. I'm taking that as a good sign.
Will we be on camera for the 2 tests, or just do those on your own?
I don't favor that option for just tests, because since I like giving tests outside of class time, so the class time can be prep and review. You can come that's the time people come with their questions. That's when you're thinking about it. So, and even in the before times, the department liked to have everyone together outside of class time, so that we were all just in test mode, you studied at the lecture, and we're just in here together, everyone has as much time as they need. I liked that model before the world ended. I'm trying to emulate that as best I can. But instead of forcing everyone to sit in front of their computer for 5 hours a particular night a week, since WebAssign randomizes the numbers anyway, I like giving students the option to spend as much time as they need at a specific block of their choosing. So for just tests, since I'm giving you the choice to take it like across 3 different days, no. But for the exam, since we have a pre-assigned time where everyone would be taking it normally anyway, yes. Okay. Miscellaneous announcements. Again, no lab this week. We will normally do a quiz and a homework every week, but just for starting things off, the first assignments will be due in 2 weeks as people are getting WebAssign access, and just do the homework before the quiz. And that is the intro spiel, which I know you're, even at the start of spring, everyone's still getting, their first couple days is always just being bogged down with syllabus and intro. A lot of that was probably reviewed from your last class. I'm thirsty and need a minute's break from talking. So, since this is about halfway through the long period, I'm going to call a quick water break. If you need refreshments or anything, now's a good time. I encourage a quick brain break. Check your notifications, because I get a ton of those overnight. Sorry, during class. Here. Maybe I should, now I'm worried.
Either because I bought it last semester, but I only bought like the 1 semester worth instead of a year's worth. And so I emailed them and I was like, hey, can I like extend this and like instead of paying $100, just pay like $25, so it's like the year went, and they said no. So, but they only brought back to me today.
Like I said, I ordered this.
Yeah, so I go like to the college website, and then it's not Cengage Unlimited, I don't think.
Wait, the college website.
I'm sorry, no, to Cengage website.
Is this, how did you get here? Just typed in, what's your note?
I'm trying to remember, okay, I just, so like go to Cengage's website, where the, because they have like Cengage Unlimited, which is more expensive, just like,
Oh, it's called college physics.
have you heard back from the med school?
Yes, so I'm in it in West meetings.
Very exciting.
So I have my decision before next Friday. Alright.
Okay, so, the digital platform, that's what you need, that's like the WebAssign. Yeah. See, if I was smart and I bought the 10-month, I would be set.
You would be fine.
Instead, I have to spend another $100. Yeah, but that's it. Cengage Unlimited is like, you have multiple classes that use this platform. My chair.
Okay. Any comments, concerns, haikus before we continue? Okay. So since we only meet twice a week, we do need to at least start the learning process. So, let's break it down. We'll look at the Brightspace page. Just to let you know that it's here. Chapter, we're jumping around in the same textbook you were jumping around in last semester. So officially, the number that matches up with that book is chapter 10 for where we're starting. On Brightspace, on each of the numbered chapter tabs, if you click on the tab itself, I'll try to put links to the recordings here for if you need them. Listed under that tab is the slideshow, the notes that I'm about to be displaying. These are here for you. You can access them anytime. And occasionally, from the start of the chapter to the end of the chapter, I might revise the slideshow somewhat, add examples, tweak definitions. If that happens, I will make sure the revised copy is also uploaded. But this is the copy I'm presently displaying. I'll let you know if I have anything. Additionally, I'm realizing I forgot to upload the course formula sheet to here. Eventually, there will be a formula sheet listed under course info, like you had before. Your formula sheet is your best friend. You can use it and your calculator on any and all assignments. And in fact, I encourage you to, because I'm paid to be a physicist and I can't remember them all. And I honestly find that not giving people a formula sheet would be really dumb, because if you were, when you're working as a scientist, you have your reference notes next to you. If you're being paid to do science, you have your formula sheet. Why would you not give that to the students? So that will be there. We can look at it once I get it live. I just need to finish it. Sorry about that, everyone. But the notes are there, and we will at least begin the introduction to thermal physics. Thermal meaning other, referring to heat and thermal heat and the energy of temperature. So, last semester you learned about energy and work. And the energy we're going to be talking about is still energy. Things that you know about energy from 1500 are still true. The statement, energy cannot be created or destroyed, should sound familiar to you, I hope. Okay, got a couple nods, very good. So, all forms of energy tend to simply just swap from one to the other. You use energy to do work, and in doing so, you tend to transform that energy and put it in a different place. If I do work to lift my water bottle, then energy inside my arm was used to give energy to the water bottle, and now it has GPE, where it didn't before. The forms of energy you looked at in 1500 were largely types of mechanical energy, which means that they had to do with the motion and physicality of objects that can be interacted with on our direct sort of human scale. Kinetic energy, something is physically moving. Gravitational potential, something has been physically lifted. Elastic, something is physically being deformed, and then it returns to its original shape. These are different from non-mechanical forms of energy, because the non-mechanical forms usually are a lot harder to see. You can see the moving object, but you can't really see the thermal energy. You can't really see energy itself, period. You can never look at something and say, that is energy. You can only see what the energy does. But thermal energy is just that much harder to visibly detect, because it's usually inside of something. Non-mechanical forms of energy tend to occupy objects in a non-standard way. Objects that have thermal energy get warmer, which again, you can't really see. And this is the form we're going to focus on now. And in a couple months, we'll also talk about energy in the form of electricity, and eventually energy in the form of waves. So, thermal energy is kind of unique in that it's the type of energy that all the other forms default to turning into. Energy can't be destroyed, it can only change form. And thermal energy is the form most energy attempts to turn into, because every single act in the universe, every single process turns some amount of thermal energy, some amount of the original energy into the thermal state. For example, when I lift my water bottle, let's say that I use 11 joules of energy doing this. There's 11 joules of energy that was burned up in my arm to accomplish this task. How much energy do you think the water bottle gained from that interaction?
In like a perfect world,
In a perfect world, sure.
11 joules.
Right. Ideally, we want all 11 joules that I used to be in the water bottle as GPE. That's the ideal setting, where we assume that there's no friction and other things slowing us down. But we do live in a world where friction exists. And even though you don't always notice it, there's friction inside of your arm. You are a machine made of meat and muscle, and your tendons physically slide across one another. That's friction. So, if my arm uses 11 joules of energy to do something, odds are less than 11 joules actually ends up doing the intended task. So, let's say I use 11 joules to lift the bottle, but only 10 joules end up in the bottle. That means 1 joule is somewhere else. And that somewhere else is usually transformed into thermal energy. Friction, by its very nature, takes away mechanical energy and turns it into thermal. The same total energy exists. The energy wasn't destroyed. It's just kind of useless now. You can feel this directly by just rubbing your hands together. It's not very cold today, but on a cold day, you might do this to warm your hands up. Why does this warm your hands up? Friction. Your hands have kinetic energy. Friction takes some of that kinetic energy away and turns it into thermal energy that just warms your palms up. The human body is really good at making thermal energy because we're warm-blooded. We're designed to transform food energy into thermal energy so that we don't freeze to death. So, thermal energy, it is a form of energy that can be possessed by the atoms and molecules that make up a substance. It's sort of internal in that it is possessed by atoms and molecules. If you give thermal energy to an object, you might not see the object change, but its atoms are going to change. It is still measured in joules, so that's the same unit you've been using. It is the same kind of, it is still energy, so all that math still applies. And when something has thermal energy, it changes mostly on the atomic level. You've studied kinetic energy, where an object with mass has energy and then is moving. Does anyone remember the formula for kinetic energy?
1/2 mv².
Very good. So, if a mass has a velocity, it has some amount of kinetic energy that is allowing it to move in that direction. Thermal energy is very similar, because on the atomic level, if you zoom in far enough to the atoms and molecules that make up something, those atoms have mass and they're constantly moving. If you think something's stationary, it probably isn't, because some part of it is moving at a level your human eye can't see. And the warmer something is, the more its molecules are jumbling about. The more thermal energy something possesses, the higher its temperature gets, and the faster its mass is moving. So thermal energy is really just atomic level kinetic energy, if you think about it. which is one reason why friction is able to transform kinetic energy into thermal energy. You're just changing what's moving. So, when an object possesses kinetic energy, it moves visibly in a scale you can detect. When an object has thermal energy, it's moving at the atomic level. Again, all the same logic applies, we're just changing the way we use it. The warmer something is, the more its molecules move, and the colder something is, the less thermal energy it has, the slower its particles are moving. What this means is, this is kind of a perspective thing that a lot of people don't talk about. Cold doesn't really exist. There is no thing called coldness. You cannot add something to make it cold. You can make something warmer by giving it thermal energy, but you make it colder by taking thermal energy away. Coldness is not the presence of some aspect of coldness, it's the absence of heat. So that's going to become very relevant as we continue doing the math for this chapter. Speaking of math, you're going to see some formulas in a minute. This is to illustrate a point, they are not there to scare you. Now, we tend to measure thermal energy by measuring something's temperature. But temperature is kind of weird in that it's not a direct measure of thermal energy, it's a measure of the average energy of the particles of an object. Now, in general, the more thermal energy you give something, the warmer it will get. That is still true. So, we took the math for kinetic energy and we began applying it to atoms to try to figure out the direct correlation there. This formula is going to be used later. Right now it's just to illustrate a point and a comparison to the kinetic energy formula. But because atoms have mass and they are moving, we were able to link the kinetic energy formula to this statement about those particles. Basically, it's hard to know the mass of an individual particle. Like if you were able to rip one atom out of something, it's very hard to just measure its mass. So if we wanted to find the kinetic energy of an individual atom, it's too hard to try. So we derived this formula instead. Basically, the higher your temperature is, the more energy is inside of the object. Again, this formula is just up here right now as a point of comparison. But if you wanted to know the kinetic energy level of one atom, all you need is 3/2 times this constant. This is a constant down here. So this lowercase k refers to this number times the temperature of the object. The warmer something gets, the faster its particles move. Now, we have that formula because you can't really measure the mass or speed of an individual atom. Our speedometers don't work that small. So we use temperature to indirectly figure their speed out. But how do we measure temperature and how does that work? There are lots of different ways of actually measuring the temperature of various devices. The one we'll be referring to most often is a thermometer, wherein you physically place the thermometer against something, thermal energy will travel into the thermometer, and that will cause the liquid inside the thermometer to expand based on what its final temperature is. So you're technically not even measuring the energy level of the other object, you're measuring the energy level that the thermometer ends up at because of the other object. Yes?
How do those thermometers that they just point at your head work? If that's how these work?
Good question. If it doesn't make contact with your body, it's probably measuring radiation. the end of the semester, we'll talk more about that, but basically you are radioactive. Everything is, and that includes humans. That sensor is probably measuring the infrared coming off of your body, which is the same technology night vision goggles are based on. Snakes can see that way too. Have you ever heard about that? Now, we say that temperature is a relative measurement. This is sort of the first math and the first formulas we're really going to be using this semester, just as a start. Temperature is a relative measurement. So, as an example, let's say that I boil a pot of water, and that water gets up to 100 degrees Celsius, because that's the boiling point of water. Now, what would have more thermal energy? That pot of 100 degrees Celsius water, or a desert that is that same temperature? The entire desert.
Water, right? Because I was going to move more freely.
Not exactly. If you have two objects that have the same temperature, if they are the same thermometer temperature, that doesn't necessarily mean that doesn't mean they have the same amount of thermal energy in the entire object. Okay, slightly better visual example. I don't know why I went with the desert one. Let's say you have 1 cube of ice. What is the freezing point of water in Celsius and Fahrenheit?
0.
All right, we got 0 Celsius. What about Fahrenheit? Very good. That's just middle school review. So that is the temperature of that one tiny ice cube. It's also going to be the temperature of this ice cube. I don't draw good. So we have two objects that are at the same temperature. Which one has more thermal energy? Okay. Good, you're correct, to ease your mind. But why? It has more atoms in it. There's more atoms that need the same energy per atom as the atoms in this. They have each atom in each of these objects has the same energy because the average across the whole thing determines its temperature, but this has more atoms, meaning there's more energy in it because each atom has the same energy as the others. So you're having a very good train of thought. What this means is temperature does not tell you energy level. It tells you average energy level for the whole object. And that's what it needs to be treated as. It is not a catch-all for this must have more energy than something else. Because that pot of boiling water would probably have less thermal energy than an iceberg. Because there's just more atoms in the iceberg. So, at least to get a tiny bit of math in your notebooks for you to start looking at your homework with, we're going to talk at least a little bit about the temperature scales we're going to be using. There are 3 of them in common use these days. They are Celsius, Fahrenheit, and Kelvin. Which one do you think we're going to use most in this class?
Celsius.
Almost.
Fahrenheit.
Less most.
No.
Kelvin.
There you go.
So, to go just a tiny bit into their history, the oldest scale is actually Fahrenheit. It was invented by a Polish man named Gabe, who was just inventing a temperature scale because we needed one. But rather than basing it on water, he based it on sea brine. I don't know why. I'm sure it made sense to him at the time. I was actually talking about this with my fiance the other night, and we looked into the story. He probably just had ADHD and he made it the numbers he did out of numerical necessity for his brain. I don't blame him. Point is, he made his scale, and it's a little weird by modern standards because water on the Fahrenheit scale freezes at 32 and boils at 212, which are 180 degrees apart. It's just a little off scale. It's kind of weird numerically. So only the United States really uses this, and I don't know why. Eventually, a man named Anders invented a different temperature scale based on not seawater and based on intervals of 10, which physics really likes because it's nice and numerical and easily divisible. But eventually we found out that something colder than 0 Celsius exists. It doesn't happen much around here, but you can get colder than the freezing point of water. So we needed a new scale that could represent that. And so a man with the title of Lord Kelvin, I assume that was a title and his first name isn't Lord, eventually came up with a new scale where the 0 on the Kelvin scale represents the coldest anything can ever be. 0 Kelvin means this object possesses no thermal energy. It is physically as cold as it can possibly get.
You watched the documentary on that?
There's a documentary?
Yeah, it's a 2-part documentary. We had to watch it last semester at Phys1510. You would like it.
Okay.
I think it's by Nova.
Who narrates it?
You would.
Hmm?
What did you say?
Who narrates it?
No idea.
That's fair. Sometimes they get like a good voice actor to do it. I'd pay to watch a science documentary narrated by Keith David. So, wait, I don't need to draw anything. The scale's already up here. So, the 3 temperature scales we have, they all measure the same thing. So, they'll tell you the same information. It's just a matter of literally scale. So, for frame of reference, in the United States, we like to operate in Fahrenheit. If you check the weather right now, it'll probably say like 60 Fahrenheit, which is colder than room temperature. On the 3 different scales, Fahrenheit, water freezes at 32. In Celsius, water freezes at 0. And in Kelvin, water freezes at 273. Something worth noting, though, if you're looking at this picture, you might notice degrees Fahrenheit, degrees Celsius, and just Kelvin. I'm still not sure why. Probably need to Google this later. Maybe it was in the documentary, but there's no degrees Kelvin, it's just Kelvin. So I'm going to say 273 kelvins if I was talking about this. And these 3 scales mean the same thing. It's just the temperature water freezes at. It's just a matter of what thermometer you're using. Then on the upper scale, we have the boiling point of water. In Fahrenheit, that's 212. In Celsius, that's 100. And in Kelvin, that is 373. What's interesting about this is, on both Kelvin and Celsius, these 2 points are both 100 units apart. That's because Kelvin is based on Celsius. It's just adjusted by 273 to account for absolute 0. What that means is, if you increase something's temperature by 10 Celsius, you also increase it by 10 Kelvin. It just makes the conversions a little nicer. So most of our formulas in this class are going to use Kelvin, since it is the best representation of the thermal energy of an object. Like with this ice cube, it can get colder than this, which means it still has thermal energy that can be removed. So most formulas will take Kelvin, but because of this like scaling, Celsius will work sometimes. There are some formulas Celsius works in that you won't necessarily need Kelvin for. But the golden rule that you can write at the top of your notebook, Kelvin will always work for the formulas I give you. Yes?
So if 98 degrees Fahrenheit is normal body temperature, why does it feel hot outside when outside is 98 degrees?
because I'm not a biologist, I'm in pure physics. So as soon as this translates into the human body, I'm talking about it as a very different lens than any of you who are pre-med. But from what I understand, this is the internal temperature of a human body inside the furnace that is your warm-blooded nature. When you eat food, some of it goes into making thermal energy so you can move, some of it goes into your organs and your brain, some of it goes into just keeping you warm so that all the biological processes happen and you don't freeze to death. But your skin is designed as a very good insulator. The human body is designed to keep that temperature in it and about 75 Fahrenheit out of it. Because 75 is roughly the average temperature most places on planet Earth, which is why that's usually the temperature most people's thermostat is set to, about 35, about 75 to 70, somewhere in that range. So across the board, about 75 Fahrenheit is room temperature, which correlates to about 25 Celsius and about 300 Kelvin, roughly. And from my best understanding, it's just the fact that between your internal furnace and the air outside of you is several layers of insulation to keep all that heat in you. And because the nerves that detect temperature are in your skin, those are calibrated to what you feel around you, not what's inside you. Yeah, you have no to my understanding, you lack completely temperature sensing nerves in your body. It's all in your skin. Additionally, those nerves don't detect temperature. They detect whether heat is entering you or leaving you. Because I have no calibration for, yes, it's 75 degrees in this room. When I touch something cold, it doesn't tell me, oh, that's 0 degrees Celsius. It just says, ow, cold, don't. Because it's not a thermometer, it's just a measure of where the heat is going. If you touch something hot, heat enters you, you feel hot. So it's based on what your skin thinks is normal, and it's based on whether heat is entering you or leaving you.
Okay.
It's my best understanding of the human nervous system and your warm-blooded nature. Okay, I at least want to show you the temperature conversion formulas so that you have them, because you're going to start looking at your homework soon, right?
Sure.
Sure. Thank you for the enthusiasm. Okay. They all measure, every scale measures the same thing, so it's just a matter of converting one to the other. So, if you are converting Fahrenheit to Celsius, temperature Fahrenheit is equal to 9/5 times the Celsius temperature. So if I was to make sure that the order of operations here is clear, that's 9/5, which I will put in parentheses, the fraction 9/5 times the Celsius temperature as it is. You need to do that before you add 32. And just to explain why each part of this formula exists, this part here is to adjust the fact that 1 unit Fahrenheit is 1.8 times bigger than 1 unit Celsius. And then this piece here is to adjust the freezing temperature, because it's just set from 0 up to 32 in the Fahrenheit scale. Yes?
So this is going from Celsius to Fahrenheit?
Right. As this is written, you can plug in a Celsius and get a Fahrenheit. So, to prove this works real quick, let's say we plug in 0 Celsius. 0 times 9/5 is going to be 0. If you add 32 to that, you'll get 32 Fahrenheit. Subsequently, if you put in 100 Celsius to find the boiling point in Fahrenheit. 100 times 9/5 should be 180 plus 32 is 212. Now, okay, this is, you plug in a Celsius, you get a Fahrenheit. I'm going to go ahead and do the work to switch that for you, just so that you have it in your notes. If you wanted to get Celsius from Fahrenheit, that would be 5/9, the fraction as a whole, times TF minus 32. You're doing the same, you're doing it in reverse order. You're subtracting the 32 first to get rid of that offset, and then you're multiplying it by the inverse of 5/9. So 2 formulas for the price of 1. And we're about at the end of the period. I don't want to hold you today. So, good thing, the last formula is very straightforward. To convert from Celsius to Kelvin, you just add 273, because they're based on the same base unit, they're the same size. You don't have to multiply to set the scale anywhere. So if you have a Celsius, you just add 273 to make it the Kelvin. In reverse, if you have a Kelvin and want a Celsius, you subtract 273 from the Kelvin. I don't have a good pre-written shorthand for Fahrenheit to Kelvin. My advice is just go through each one at one time. So, those are our official first formulas of the class. A formula sheet with those on them will be uploaded soon. I do recommend you go ahead and look at the homework. As soon as you open the tab, it'll be easier to come back to later. At least I found out with the way my brain works. And if anyone, unless anyone has any questions, then I will see you all today. You have a great day. Good first week back. Stay hydrated, stay healthy, stay on. Sorry? Yes, I would vote that. I would vote that a lot. I was leading into stay inconvenienced by the weather. It was raining earlier, but alive is also good.
It stopped raining on my way in.